So we are making good progress in our program of non-parametric Bootstrap. We have been able to approximate the underlying CDF with remarkable accuracy using the empirical cumulative distribution function based on the past data. Now comes the next hurdle, namely we have to simulate future data from that empirical cumulative distribution function. Now the problem is this. R or any other statistical software can generate random numbers from standard distributions. Now ECDF depends on your past data, so it cannot be considered a standard distribution. It does not even have a nice simple formula. So how can you generate data from the ECDF? All that we know is that it is a step function. Starts from 0, ends at 1, finitely many steps, that's all. The steps are not even equally spaced, there may be uneven heights, all sorts of things. How am I going to generate data from ECDF? Turns out that there is a very simple way of doing that also. In order to understand that, let's start with a simple CDF, which is a step function. So I take this thing. So in this case, what I have is that I have got certain steps at 1, 2, 3, 4, 5 and 6. And at each of them I have a jump. It starts at 0, it ends at 1. And to make the discussion simple, I will assume that all the jumps are of equal height. So 1, 6, 1, 6, 1, 6 up to 1. Suppose I ask you to simulate random numbers from the distribution corresponding to this CDF. It might look complicated, but if you think carefully, you will understand that this thing, any random variable that follows this distribution can take only the values 1, 2, 3, 4, 5 or 6, and the probability of taking one value is this height, 1/6. Probability of taking the value 2 is this, probability of 3 is also 1/6 and so on all the way up to this, which means that it is nothing but our very familiar die. And that is very easy to simulate from. How do I do it using, say, R? All that I will do is, I will start with a list of these numbers 1, 2, 3, 4, 5, 6, our sample space, and then just draw a simple random sample out of them. So each one of them will have equal probability 1/6, 1/6, 1/6. That's it. And if you want to roll the die, say 10 times, then I just draw a simple random sample with replacement from this set. Remember, I have to do it with replacement. I cannot draw 10 numbers out of this 6 without replacement. And if I get 2 once, I might get 2 later again. So I have to draw just a simple random sample with replacement from this sample space. That's it. So generating from this step function at least turned out to be pretty easy, either by using a physical device or by using a computer. Now you might object that, well, here I used the fact that everything was equally spaced, all the probabilities were same. That is not going to be the case for, say, empirical cumulative distribution function. There it may very well happen that this 5 that we see here is actually not present. Instead, I have got multiple copies of 3. That is possible. Right? It is quite possible that they are not equally spaced. And similarly, if I do this, if I take this 5 to this 3, what will happen? The jump at 3 will be more, and as a result this will also push up. So the entire part between the 3 and 5 will push up one step. And this will be the cumulative distribution function. So suppose my ECDF turns out like this. How do I simulate from that? Well, again, the same idea holds. Understand carefully. Now my sample space does not contain 5 anymore. It is 1, 2, 3, 4, 6. However, in my sample, 3 has occurred twice. So what I will do is that instead of writing down the sample space, I will write down all the values that I have seen in my past data as a list. I allow repetition. So maybe the first value was 4, then the next value was 3, then I saw 6, then I saw 3 again, then 1 and then 2. So I write them in that list and then I pick one of them at random. As a result, because there are 2 3s, the probability that you will draw a 3 will be actually 2 by 6, and that corresponds to this increased height. So you see, you really do not have to worry about the fact that this has come twice, so I must assign more probability to it. You just make down the list, you just write down the list of whatever is your sample, your past data, merely pick one randomly. Give everything equal probability. If a value occurs multiple times, then that value will get higher probability because it occurs here as well as there. So, if you want to generate a sample of say size 10,000, from this all that you do is you draw a simple random sample with replacement, not without, with replacement from that list. The list will contain repetition. So you just take your existing sample from your past data, you draw a simple random sample with replacement of whatever size you like, and then you get basically a corresponding size sample from the empirical CDF. And this you can very easily carry out using the function sample in R. So you see, ECDF is a wonderful tool. It does estimate very precisely the underlying CDF, and at the same time it is super easy to simulate from the ECDF. So it is a very powerful tool. It's a pity that in undergraduate courses it is not given that importance. We give more importance to quite useless stuff like ogives and things like that, which are never used anywhere. But ECDF, which is much more useful, has wonderful mathematical properties, is hardly discussed. Okay, so now you see how we proceed step by step. We basically just take our original sample, draw a simple random sample with replacement, treat that as a future data, and we can proceed. Now before we go to work with R, let's consolidate our understanding as to the steps of non-parametric Bootstrap. The steps that I am going to outline now are the most important steps in this entire talk, because these are the things that you have to do again and again. So step 1, of course, you can even call it step 0, is that you start with the original sample. That is your past data. So you start with your past data. Now what do you do? You draw a simple random sample with replacement from that, which effectively, from the viewpoint of statistics, what you are doing is you are generating a random sample from that empirical distribution function. Now notice that I have said draw a simple random sample with replacement of the same size. That is very important. I have heard even professors of statistics wrongly say that that is not important. It is very important that if your original sample is of size 100, then your simple random sample with replacement should also be of size 100. Now why is that? Because remember, you are trying to mimic your original sample. Whatever you have done with your original sample, you want to see if you do the same thing with future data. How will your method behave? So you do not want to change anything that is under your control, and sample size is one of the things that is under your control. So do not go overboard and think that, well, my original sample required actual resource, so I could not get more data, but here I am just generating them using a computer, so now I will generate a huge data set. No. If your original sample was of size 100, generate a sample of size 100 here again. Now the next thing is, now that you have this new data, you apply your method do that. That is, of course, something that you already know. So you apply your method and you check whether your method is good or bad. You must be having some criterion by which you will check whether it is successful, whether it fails, how well it performs, what is the amount of deviation, etc., etc. You do that and make sure that you keep track of this, because we are going to do it again and again. So make sure whatever you get for this Bootstrap sample, so the thing that you got here is called your Bootstrap sample or Bootstrap resample. You are going to do that again and again, so keep track of that. So these 3 steps you have to do repeatedly, because you are trying this again and again to see how it performs. So you put them inside a loop. Now, how long do you want this loop to run? Well, there is no exact bound for that. I have written 1000, you may do it 10,000, doesn't matter. Here, there is no problem if you do that again and again. So that may be 1000, 10,000, 1 million, as much time and resource you have. You can try to do that. But make sure that every time you draw a sample of the same size as your original sample. Now, again, I must make it clear that when you are doing it again and again, you are basically trying to see the average behavior. Now, using this average behavior, what you will get is the behavior of the empirical CDF, because you are generating everything from the empirical CDF. And remember, the empirical CDF is not exactly same as the underlying CDF. So that difference is not going to go away merely by increasing this 1000 to something. That difference can be reduced only if your original sample size can be made larger, which, as any statistician knows, is always a desirable thing. Having a larger sample is, of course, a better idea. So you already have one sample, you do not have any further control to change that. So Fn hat, the empirical distribution function, let's call it Fn hat, and the underlying CDF F, that's already a gap. You are not reducing that gap. You are merely getting a better and better and better picture of Fn hat. So increasing this 1000 tremendously is not of much use. So it is something like this. Suppose there is a measurement and someone has made a copy of that measurement. Say there is a length and someone has made a rough sketch of that length, which is correct up to the nearest centimeter. So the true length and your rough sketch, they match up to the nearest centimeter. Now you want to measure that rough sketch to get an idea about the true length. Now if the rough sketch itself is correct only up to the nearest centimeter, it is completely meaningless to measure that rough sketch up to the nearest millimeter, right? Because the main error, the main source of error will be the difference between the rough sketch and the actual thing. So, of course, if your error is something of the order more than 1 centimeter, that is bad. But once your measure of error comes down to the order of a centimeter, there is not much sense to increase the accuracy any further. Similarly, here also, making this number tremendously large, like 10 billion, will only waste your computer resource. Something like 1000, 10,000, okay, that is fine. Of course, no one can give any such hard number. It depends on the problem. But remember that making this number enormously large is not going to achieve anything for you. Okay, now that you have run this loop, say 1000 times, so in each pass, you get one performance score. So you generate a data set, see how it performs. You generate another data set, see how it performs. Keep track of all those things, and finally, coming out of the loop, you aggregate them. I deliberately keep these two steps vague, because they may be adapted for different situations. So how you track performance, that may be something as simple as storing a value, and this aggregating may be as simple as making a plot or making an average, taking standard deviation. Somehow you have to look at the overall behavior of all these performance coefficient or scores that you have obtained. So with this in mind, we are going to approach R, where we shall see a practical implementation of this concept. Now we are going to see how our algorithm of non-parametric bootstrap is going to work in practice. So here's my example. Just to compare it with the earlier things, I will work with again random normal data. So here is my raw data, which I have generated from from the normal distribution, standard normal distribution, sample of size 1000, and I will start by plotting the ECDF. So let me just do it. Plotting the ECDF, so the super job. Okay, and on top of it, we have already done that just to see that everything is okay. Yes, they are also very nice. Now I am going to generate my data from the empirical cumulative distribution function, which reduces to just drawing a simple random sample with replacement. That's what I am doing. Here's my raw data. I am putting that inside the sample function, which is the function to carry out simple random sample, and I want it to be with replacement. I have written rep equal to t, that is replace equal to true, and the size of the sample that I want must be the same as the sample size of my original data, which is 1000, but instead of writing 1000, I have written it like length of raw data, just to remind ourselves that these two sizes must be the same. Okay, let's do that. And I have got lots of numbers. We may take a look at them. Resample data. Lots and lots of numbers. All these numbers are numbers that were present in my original data. Some of them are repeated. So in order to see that, let's just look at the histogram. So the histogram, what do we expect it to be? It should be like a normal thing. Because though we have not generated it from normal, it should be approximately normal, very closely normal. We should not be able to see the difference just from the graph. Let's see. Well, I did the histogram. Yes, it does look like the bell-shaped curve. Just to be doubly sure, I am going to overlay the standard normal density on top of this, minus 3 to 3. I put add equal to true. Let's put a color also. Color equals red, line width equal to 3, just to make it stand out. And yes, it is indeed very close to it. So I generated my resample without the knowledge that it comes from a normal distribution, but still it works. So even if it came from some very weird thing, some bimodal thing, partly discrete, partly continuous, all sorts of bad things, even then you will get the same behavior. So that's the beauty of it. Okay, so I have generated one data and I could get it. Now of course that's not what I have in mind. I want to do it again and again and again and again. So I want to find out, say I want to find out the sampling distribution of x bar. So here is my random sample. I am going to compute x bar from it, and I want to know what is the sampling distribution of x bar. I do not know the underlying distribution. I want to still get the sampling distribution. So I am going to run this loop a large number of times, and I will call it, take the value 10,000. So I will do it 10,000 times. So I am going to get 10,000 different x bar values. So I allocate my space x bar equal to numeric 10,000. Then I will enter the loop for I in 1 to 10,000. In every pass of the loop, I generate my bootstrap sample. I just call it x this time. Sample, raw data, length of raw data, rep equal to true. So this is precisely the way we computed our resample data, except that we are now doing it inside the loop. Once we get this resample data, which is x, I compute its mean, or whatever statistic you have in mind. It may be a very complicated statistic for which you have a function. Just invoke that function. The value that you get, keep track of it. That is, you save it in your x bar array. X bar I. In the ith resample, I got this value. So I will just run this. So I am running this. Well, it just did it in the twinkling of an eye. And I have got my x bar. So now I am going to aggregate. So what's x bar? If you quickly look at it, this is actually 10,000 numbers. All the averages that I have got, 10,000 numbers. Okay, now we want to get the aggregate behavior. The simplest way of getting an aggregate behavior will be just draw the histogram. So let's do that. And the histogram turns out to be this. Now, since it is a simulated study, so we played God initially. We created from actually a known distribution. So I know that my original data was from normal 0, 1. Size was how much? 1000, right? Size was 1000. So what would you expect? The mean to be of x bar, mean again 0, and the standard deviation should be 1 over root n, that is 1 over square root of 1000. So the histogram that you saw just now of x bar should be like the density function of normal 0 and standard deviation 1 over square root of 1000. So let's just check that by overlaying this curve d non, and I am using this x. Don't be confused about this x and that x. When I am using the curve function, it just plots a function, and the function must be specified with dummy variable x. So this x is the dummy x. From this to this, I am adding it. So I will just do it, and yep, not very good, I must say, but it is something. Now you might be wondering, what happened? I did 10,000 and it shifted a little bit to the left, right? Yeah, the reason is that your original sample, when you drew your original sample, that was possibly a little biased. That is quite possible, right? Now, when you do this again and again and again and again, obviously you are always resampling from that initial biased sample. So if there is a bias in your initial sample, bootstrapping is not to cure that. Remember this. So as I say, bootstrap is one way of reusing your past data to sort of as a lame substitute for future data. It is not true substitute of future data because it is, after all, based on the past data. If there is any bad feature in the past data, it will stay. Possibly to a reduced extent, but it will stay. So the trouble of using the past data as a direct proxy for future data still persists to some extent in every resampling technique. No resampling technique should ever be considered as a complete substitute for future data. And this example shows it. I will just rerun it, and because it's random and it might just as well go away. So let me just do it. In order to do that, I'll have to generate my sample. Well, I will just quickly see what was my original mean. Mean raw data. So you see, mean raw data was already a little bit towards the left, and that is what was reflected. So I will just redo this thing. I will generate this, and then I will carry out this step once again, and this and this. Take a look at this. Well, this time it has shifted somewhat to the right. So you see there is some amount of variability in this thing. So this is instructive because this amount of variability is still inevitable. Okay, so this is to jolt your faith to some extent to Bootstrap. Sometimes people just consider this as God. Whatever is given by Bootstrap must be correct. No, that is not true. Okay, so whatever you have done so far was something for which you knew the sampling distribution. And I have shown you something else also. Suppose you are interested in just the standard error of x bar, you can try that also. You just do SD of x bar, and if you do that, you get 0.032, etc. Ideally, it should have been 1 by square root of 1000. So it should have been 0.031, etc., 0.033. Not very bad. Okay, now let's try something where we really cannot find out the sampling distribution without using Bootstrap. So something really complicated, something for which you can write down the sampling distribution. I will work with the trimmed mean. Now I hope all of you know the trimmed mean. It is same as mean, except that when you have your data, you chop off some of the extreme observations. So if I say 10% trimmed mean, this means you sort all your data, then trim of 5% of this extreme and 5% of that extreme. Whatever remains, take average of that. This is more robust than usual mean, because sometimes because of some typo etc. you might get unusually small values or unusually large values. They might pull the mean towards themselves, but if you trim them off, then you get something which is more likely to stay in the center. After all, mean is supposed to be a measure of central tendency. If it goes too far out to one extreme, that's not good. So it is more robust than mean and more sensitive than median. So, but for trim mean, it is very difficult to come up with a theory because of this chopping thing. It is not easy to deal with it mathematically. So if I want to compute the trimmed mean and I want to find out its standard error or its sampling distribution, then Bootstrap is typically the way to go, and I am showing that. So again, I will be working on the same, based on the same random sample. So I start with allocating memory, x bar t for trimmed, and numeric, I will do it 10,000 times. Then I say for I from this, I generate my resample, and I perform trimmed mean computation. In R, you use mean, but with this extra parameter trim equal to 0.1 means 10% trimmed mean. So chop off 5% here, 5% from that extreme, and then compute the mean. And I proceed exactly in the same way as I did last time. I will form the histogram of that. So I will take the histogram, and this also looks pretty normal to me, except that now I do not have a very clear-cut theory as to what should this distribution be, because unlike normal mean, which was mathematically amenable, but it is possible to overlay the very same curve, it will be basically the same thing. Let me just try. So again, the same thing, that slightly shifted version that we saw earlier. And I can find out its standard error by using SD command. So if I am using trim mean, I can find standard error like this. There is no analytical formula that I know of to compute the standard error of trim mean. And you can understand it is perfectly general. Instead of computing trim mean, you think of whatever method you have in mind. Just put it there and you can get mean, you can get standard error, you can get various probabilities. For example, I may be interested in knowing, say, what is the median of all these trimmed x bar values. I can find that. I will just type median of x bar t. So I have estimated the median of trimmed x bar, the median of the sampling distribution. I might want to know what is the probability that this value exceeds a given value. What is the probability that this mean will exceed the value 0.05? I can find that very easily. I can just say mean x bar t greater than 0.05, and it is 35%. Let's understand this. X bar t greater than 0.05. If I just type this, it will give me a long list of true, false, true, false, true, false. Out of those 10,000 cases, it checks, is it greater than this or is it less than this? Greater than, less than, greater than, less than, true and false, true and false. Now all the truths inside the computer are encoded as 1 and all the falses are encoded as 0. So when you take mean of them, you are basically computing the proportion of ones, that is the proportion of times that condition holds. That is why I could compute that thing. So this was, the probability is 0.35 approximately that the sample x bar mean, the sample trimmed mean will exceed 0.05. So you can do whatever thing comes to your mind using the same basic Bootstrap loop. So that's basically all that I wanted to show in this particular session. Now the thing that I want to impress here in your mind is that once you understand this basic loop, Bootstrap is very general. That is one of the greatest beauties of Bootstrap. It is very, very general. It does not matter whether the particular statistical method that you are trying to assess is a completely ad hoc one, based on heuristics, based on classical probability theory, or whatever. You can just put this into this Bootstrap machinery and find out its expected value, its standard error, probability of exceeding something. You can get confidence intervals. So let me show you how you can get confidence intervals. That's also pretty easy. So suppose I want to find out the confidence interval, say 95% confidence interval of X per trim. All that I do is I will take the so I say 95%, I will find the 2.5% on this side, 2.5% on that side. So I will use the function quantile, and I have to give X per t, and the probabilities will be, I need two of them, so 0.025 and 0.975. So I see that 2.5% quantile is this, 9.75 per quantile is this. So my confidence interval for X per trim, it must lie between this value to that value. Absolutely simple to work out. And you just name your quantity and name your confidence interval and you will get the value. So its utter simplicity and generality is what recommends Bootstrap. But do not forget the fact that Bootstrap is using something not entirely justified. It is using past value as a proxy for future data, which is not something that you should do if you can get future data. Okay, so that's basically all that I wanted to say in this session.